and gentlemen. Today we are excited to present to you how Primex technology can enhance the efficiency in your construction as well reduce the CO2 emissions. So my name is Karol Franaszek. I'm a project sales manager responsible for the Polish market. And although I'm working in Primex only for 6 months, I had a pleasure to cooperate with the company for more than 2 years, as we've been executing the battery factory for Novo Energy in Gothenburg together. So
Yeah, and hey, my name is Andis Kregers. I'm a structural engineer at Primex.
okay, so I will start with a short introduction of our company. Primex is not a new company, it's not a startup, it's a company with traditions. It has been founded in 1997, and since then we have the same ownership and leadership in the company, Mr. Yanis Osleis. So Primex is a research and design company. We are offering wide range of services that are connected with concrete slabs, elevated slabs, and other structural elements. Innovation in concrete design is at core of our business. That's why we are running the largest privately owned R&D center in Northern Europe. We are backing up our knowledge and experience on real data, real life data. That's why we have conducted over 20 full-scale tests by now. And our technology is recognized and appreciated globally. So in fact, we got our first award for Innovative Product of the Year in 2012 in Las Vegas on a World of Concrete event. So as you can see on the map above, we have a truly global presence. Right now we are almost on all continents. By now we have executed more than 25 million square meters of floors and additionally other structural elements. We are proud to be able to cooperate with the biggest and most recognized companies in the world, as you can see below. Our technology is tailor-made for complicated appliances like data centers, gigafactories, logistic hubs, and heavy industry as automotive. So now I would like to explain a bit what is the science, or as I like to call it, the magic standing behind the technology. So Primex has developed and patented a solution which is called steel fiber reinforced self-stressed concrete. And how does it work? So the technology is based on a carefully controlled expansion of the concrete, which is mixed with steel fibers. And this expansion of the concrete is introducing the tensile stress into the fibers. And this tensile stress later on is introducing compressive stress into the concrete. And this is producing the phenomena that is called self-pre-stress. Additionally, our technology also deals with shrinkage. And as you know, shrinkage is creating all the negative effects in the concrete. So thanks to this and thanks to the chemical self-stress, we are removing those negative effects. So due to this, as I mentioned, our cross-section of the floor has much higher load capacity. Thus, we can reduce the thickness of the slab and we can reduce the usage of the material. And thanks to this, we are saving CO2 emissions up to 70%, and our floors are lifetime flat due to the fact that we are dealing with the shrinkage. So now I would like to show you one of the examples of appliances of our technology. This will be the project that I'm particularly proud of, as I was the part of the construction team executing this project in Gothenburg. And this appliance is the elevated slab based on the combi deck. So I'll bring you some numbers. As you can see on the photo, this project is quite impressive. The size is 170,000 square meters. The structure of this project was mainly a prefabricated steel structure and additionally some glulam. What is very important assumption on this project was that we will achieve full composite action between the steel structure and the concrete slab. So this project was challenging indeed. As you know, the battery industry is very competitive. So to be successful, speed is an essence. And additionally, the battery industry is developing so quickly that at the beginning, we didn't have an idea how the production line would look. So it meant that our structure had to be very flexible for future changes. So actually we had to start the construction without finished design. And we've been very deep into the construction when we had the first design ready. So to bring you some specifics so you can understand this project, I will describe how the slab was designed. So the spacing between columns was 7.5 by 16 meters. Spacing between the secondary beams was 2 meters. The load assumed on this slab was quite high. It was 10 kilonewtons per square meter, so it was quite a challenge. And as I mentioned, we assumed to have a full composite action. So fun fact, to achieve this full composite action, we had to weld shear studs, as you can see on the picture, on the top of the beams every 15 centimeters. So the fun fact is that we bought all available shear studs in Europe to make this project, and additionally we had to ship some from United States. So now I'd like to ask you a question. As you're experts in concrete, what type of reinforcement we distinguish on the slabs? Probably everyone knows, right? There is bending reinforcement, shear reinforcement, and so on and so forth. But from my experience, there is one more reinforcement that exists, and this is, I like to call it psychological reinforcement. And from my experience, this reinforcement is the hardest to optimize. So I'm a perfect example of person that requires psychological reinforcement. I have a master's degree in civil engineering, specialized in reinforced concrete. I was working with it for most of my career. So when Primex came and said the first time that we can reduce most of this reinforcement, I said, like, I went to my boss and I told her, like, hey, this is not possible. We cannot do it. It won't work. Thus, the reality has proven that it works, and it works exceptionally well. So our technology can bring us from this heavily reinforced traditional slab to this. So as you can see, only traditional reinforcement left is a mesh that is above the primary beams. And yes, this is ready reinforcement just minutes before casting. But recently, we also made some measurements on this project, measurements of deflections, and the results are better than we expected. That's why right now we are working to optimize the reinforcement to achieve this, which means zero traditional reinforcement on such a case of project. So now I would like to bring you some data and show you the numbers. So the basic design on this project was 200 millimeter thick slab with 230 kilos of reinforcement per cubic meter. And thanks to our technology, we've been able to optimize the traditional reinforcement to only 40 kilos with some addition of 30 kilos of fibers. So we went down from 230 kilos in total to 70. Okay? So it's not only our technology, it's not only the optimization of reinforcement, it also brings some other benefits. So in this case, we could make large panels with no dilatations up to 2,500 square meters. We sped up installation, of course, and of course we reduced tons of CO2 emissions. Additionally, this slab is ready for future needs because it's perfect for automation. So in summary, with the reinforcement, we've been able to replace flexural bending reinforcement, shear reinforcement, and crack control reinforcement with the fibers. And only reinforcement that has to be preserved as a traditional was the reinforcement that is transferring the composite action shear forces from the structural steel beams to the concrete slab. And now I would like to show you the numbers specific to this project. So the result is, as you can see, we've been able to reduce almost 2,800 tons of steel on this project. So it's 70%. Okay, I'll let it sink in. 70% of reinforcement was reduced. What does it mean? It means that we've been able to reduce 6,000 tons of CO2 emissions with zero additional cost. And it means that if you don't have to place those 2,800 tons of steel, it means that you can save work for 41 guys through 8-month schedule. So you can imagine how the cost reduction looks in this case. So summing up, what we can bring to you on your projects. It means that from the execution standpoint, it's a true game changer. So reduction of the traditional reinforcement changed totally the process of execution in terms of material usage, resources usage, CO2 emissions, and you can also calculate what does it mean for the costs. So additionally, we are also reducing the risk on sites, because if you don't have reinforcement, it's much safer for the workers. We are improving the durability. We are reducing the shrinkage cracking. We are extending the fields with no joints, and of course we are reducing the environmental impact. So now I would like to pass the presentation.
Thank you.
Thank you.
Yeah, I would like to tell you about full-scale test in Prologis project in Sweden that was done last year. So the main goal of this project was to understand how premix slab on ground behaves at the joints. And our hypothesis was that current guidelines underestimate floor slab capacity at these joints when the joints are tight and has very little joint opening, and there are a high amount of steel fibers. And for that there was loaded real premix slab with worst case for warehouse loading, racking leg simulations, which is 2-point loads placed very close together, like 25 centimeters, and placed very close to the dowel joint. So a little about numbers. For this project, the racking one leg load was in serviceability state 80 kilonewtons. And for the worst case, for the most strict reliability class, the maximum ultimate limit state load could be 120 kilonewtons. And to achieve these loadings, there was made special steel frame, and on the steel frame was put a lot of heavy steel plates. And until at SLS state there was no problems, then the test keep on going, then we reach ULS, this 120 kilonewton loads per one leg, still no problems, and luckily there was still some steel plates left, and the test keep on going. And unfortunately, when the load on the one leg was reached 151 kilonewtons, we ran out of steel plates, and then we had to stop. But it could go on, and the results of this test, even after this maximum of 151 kilonewton 1-point load, was that the cracking width was only 0.2 millimeters, and when the slab was unloaded, those cracks closed. And another very important parameter that was measured in this test was this load transfer efficiency, which basically means when the slab is loaded on one side of the joint, how much load can be transferred through dowels to the unloaded side. And even with this maximum load that was achieved in this test, which was available to do in this test, the load transfer efficiency was over 80%, which is a really good result. And from that we can conclude that dowels work as intended. There were no failures in these theoretical model possibilities, like dowel would punch out or slab at the edge would fail. And this also proved that we can go without slab thickening in these places, and that also these crack width were very little, and they happened far beyond this serviceability limit state loading. And how it was possible? It was possible because our slab has small joint openings, and we use high steel fiber amount. And it is important because it allows for slab to be built without the local thickenings and local or full slab thickenings, or and has ability to improve joint capacity, and these joints stay flat, and it doesn't create problems for these warehouses where a lot of forklifts drive over. Yeah, here you can see the main reinforcement was steel fibers, and joint was almost with a very, very little opening. And these joints were double joints with steel plates, and they are like every 600 millimeters placed. And to sum up and to tell about premix advantages, which was the slab, that this premix has a special technology that allows these small joint openings, and we use high amount of steel fibers, which is very important in this particular case in the joints, which allowed to minimize dowel moments. Because the joints are closed and there is a very minimal bending happening in this dowel. And another thing is, as joints are closed, there is a lot more critical parameter, which allows for improved joint performance. And as we have high amount of fibers, it improves the strength of the slab. And this all sums up in that we can have thinner floors. There is no need for local thickenings. As joints are closed, we don't need to use complex and expensive joints like signage joints. And overall, we reduced material costs. And at the end, we reduce CO2. And if we zoom out further, in design and construction, we simplify works, we simplify design, we simplify works for casting, for groundworks, and we can optimize floors. And if we look from business perspective, this means there is less material used, there is fewer man hours, the faster production, and most importantly, that with every millimeter that we can save, we instantly reduce CO2. And as these warehouses are large and there are many, we at the end of the day, it adds up to a significant amount of CO2 we have reduced. And at the end, I would like to say, if you're more interested, you can find in YouTube more videos about this full-scale test and other full-scale tests we have done. And yeah, I'd like to say thank you.